All right, let's talk about breadth first and depth first search, which is the other topic this week. This is a type of tree traversal algorithm, and first we need to distinguish between setting up a problem and solving it. So we talked about a lot in the first video about terminology and graph ADT. That is basically a structural setup of some kind of an issue or a problem. And you'll see the book talk about, and examples we use, talking about shipping routes or supply routes or airline routes or anything like that, where you have a bunch of nodes connected with some distance or weight between them that represents some kind of cost, like it's mileage or distance or fuel or something of that nature. And so it's an expense. And the idea is you want to minimize the cost to go from one place to another. Now there's all kinds of algorithms to do various traversals for various purposes. That example is only one example of a cost minimization, and we'll get to that a little more next week actually. But the simplest traversals are just aimed at at searching for a solution without respect to particular weights typically. So that's depth first search and breadth first search. Let's talk about depth first search first. So depth first search, I'm going to use a tree example here. The book goes through, I'll actually go through both examples, but the tree example is simpler to show at first so you get the hang of it. And then I think once you get the hang of it, you transition it to a graph. And it's a little bit hokey at first just to start on a graph and try to understand. So here's where me pointing at things I think comes in handy. So with the depth first search traversal, the idea is, as the name implies, you go down the depth before you go across the breadth. So for depth first search traversal in here, you go A, and then you go to B, and then you continue going down. It doesn't really matter which one you pick, so you might pick B or C, or I'm simply picking left out of standard. It's not that you have to pick the leftmost node, so you could choose in your depth first search to go C and then G, or C and then F, as long as you're consistent. Actually, C and F is not really a good example because you switched right to left. So usually it's always pick the left, always pick the right, always pick the first node that's connected, something like that in the algorithm. So A to B, B to D, D to H, H to L, L to N, N to O, O to P. So we keep going like that. And when it gets down to P, there's no more nodes, so it stops. And now you go back up to A again and take the next route down. And so the next route down from A is, I'm sorry, you back up to the next, since the recursive algorithm, you back up to the next thing with a node, which is D. So D, and then you take I and M down. And then again, when I and M are done, you back up to B, and now you take E and J down. And then when J is done, you back up and take K, back up again to A, take C, F, back up, and G. You may recognize this. This is actually a pre-order traversal that we learned when we were talking about binary trees. So depth first search actually mimics a pre-order traversal on a binary tree. But of course, depth first search is also useful on a graph structure itself. So on a graph structure, which is not really a tree here, where you can have multiple things going any which way and cycles and whatnot, then depth first search does the same basic premise. So you take the first, let's say the first edge, which let's say is C, traverse it, and you take its first edge, D, traverse it, take its first edge, let's say that's E, and traverse it, and now we're at dead end. So we go back and take its second edge, since we already traversed the first one, G, its first, H, its first I. Then we go all the way back up to C here, I think we were at, and then that's done, so we go back up to A. Now A had one more D, but when we traverse that, we'll notice that we already looked at D because we marked it as visited, and that's where the visited thing comes in handy. So we go back up here, and now go back to B and to F, and now we've explored the whole graph. Again, the idea is you're looking for a solution, and depth first search will always find a solution as long as a solution exists in the graph, and the graph is not cyclic, and or there's a couple different conditions. So if the graph is cyclic, for example, let me take this and go back up to here, and then there was some other cycle that took J back down to there, notice the depth first search can go in infinite loop. But as long as you use the marked and is visited check, then you'll know that, so you won't ever do that. So if you use marked, the depth first search will always terminate, and will eventually go through your whole graph, always find the solution. Depth first search is obviously best when your solution can be deep down in a particular branch, which you don't always know that. But oftentimes, when you're looking for any solution, depth first search is a quick and easy algorithm to write. There may be many solutions. It may not be just one solution, particularly if you think about gaming and pathfinding going between 2 points, there may be that there's a lot of different ways to get there, and you really don't care which way is the best. For airline routes, maybe you do. Maybe you care that you have to go the most optimal route because you don't want the passenger sitting around for 8 hours. But in many cases you don't, and in those cases where you simply want to find a quick solution, depth first search is a nice, easy algorithm to write. And the reason why is because you can write it recursively, right? So this is a very simple recursive algorithm where you check the current node, is it the solution? If it's not, then recurse to the first item, or create a while loop, and then go through each edge and recurse that first search on its edge. And so that's it. And it's just a couple lines of code, really, to do that. So check, and if it's not, then create a loop over all your edges and recurse on each one. And then the recursive case will go down and continue to search across each of its children, etc., etc., etc. And since it's recursive, you can also implement this with a stack and a straightforward for loop or while loop if you are not as comfortable with recursion or you want to stay away from recursion. I know recursion is still baffling to some of you, and that's fine. Recursion isn't always the best way to go about things anyway. So you can use a stack to do this in the same way, but basically you push and pop on the stack. So you take the first node, check if it's the solution. If it's not, then you push the first edge onto the stack, which is the edge here. And you'll push all the edges on the stack. Push this edge on the stack. Now you're done pushing all the edges. Now pop the first one, which will be, C, actually, in this case. And then you do the same thing. Push, pop, C. So I've actually created an algorithm where I'm going this way, but you understand the same basic premise. And then when you're done with G, because there's no more, then it'll pop the next one off, which is F. And that way, you can actually pull and pop off all the items of the stack and perform a depth first search to find the solution. Now there's another advantage to depth first search, which is you don't have to write it using a tracking mechanism. You don't have to write it using a stack. You can write it recursively, and you can write it without using this isVisited notation that we were talking about. And why would you do that? There are many cases where you might want to do that to save the memory. Because if you're not using a stack, you're just using a recursive call, then there is, yes, some memory overhead, but it's less than using a full data structure to hold and keep track of all the places we haven't yet visited and the to-be processed nodes. And it's hard to give you an example of this without fast-forwarding even a whole class into an AI class, but basically when you're looking through a game search space, for example, in chess, and you're expanding upon possible moves, you can do this on the fly and create states without having to store them all, and there's a lot of them. In many cases, search space is huge or close to infinitely big, and you don't have time and space to store it all, basically, because if you stored it all, it would crash your program. In these cases, depth first search is extremely quick, and it doesn't require storage, which is a huge, huge advantage. Okay, breadth first search. Now, breadth first search is a simple level traversal, which is, as you learned the other week in binary trees, straight across. So a breadth first search traversal is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Fairly straightforward, right? And it's very easy to see in a tree structure, but it can be a little more confusing in a graph structure. So if we go to a graph, now here you have to think a little bit with breadth first because it's the same basic principle. You take a vertex and it's basically its siblings, which if you recall from terminology on trees means it's common parent but different edge, right? So A to C, you might choose this one first after you choose A, of course. So look at A. Actually, let's go with B because we already went that way, right? So A to B, and now we go to B. And when we're done with B, if we find B is not the solution, we don't go to F, but we back up now and we go to C because it's another sibling of A. And we check to see if C is the solution. If it's not, then we check to see if there's any more siblings. There's one more, which is D. So we go to D and check. And now that we're done with all those, now we take the first one's child, since there's no more children of A, which is F, and we'll check there, and that's a dead end. Now we go back and check C, take its child, which is D, but we already visited that, so we're done there. And then we go to D and its child. Let's say we go to E first, and we're done there. Let's say that's not the solution. So then we back up and take its next child, which is G, and then so forth down, because that's the only route down. But notice we'll do all of C, B, and D. We take the breadth first before we take the depth down a single path. That's really the critical difference there. So breadth first search makes use of a queue rather than a stack. if you think about the data structure, so we take A, and now we take and put its edges into the queue. So we put B in and put C in, and then we take, and then once we're done putting the edges in the queue, we dequeue the first one, which would be B, and we put all of its children, D and E, and we take the first one, we put D and E in the queue, and then we take the next item out of the queue, which if you recall was C, right? With B, C, and then D and E. So now we look at C, and we put all of its items in the queue, F and G, take the next item out of the queue, which is D, and so on and so forth. Because of that, you can't really write BFS, or breadth first search, as a recursive algorithm because it doesn't correspond to any simple break up the problem with down. But you can very easily write it with a queue structure by using a simple loop like I just described. So in each case, you check to see if the vertex is the solution. If it's not, then you add each of its edges to the queue, and then you repeat. Pull out the first vertex first, then check the solution. If it's not, add all its children edges to the queue, and repeat down. And that way you perform breadth first traversal. But because of that, breadth first search requires the queue, and because it requires the queue means it has to use this vast amount of memory. So in a tree structure, this might not seem much to you, but let's say you have a bazillion more general tree or a more general graph. We have a bazillion little guys coming out of each vertex. You could have a huge number of edges coming out of a vertex. In that case, breadth first search has to keep track of all these at each level. And so even if it has to go down just a couple levels, there's a huge amount of memory that it has to keep track of. So breadth first search has that disadvantage of not being able to operate after a couple levels with huge numbers of memory. So you have to think about the problem and the solution you're looking for. If you're looking for any old solution, breadth first search might be quicker, not require all that memory because it just simply chooses one path and just goes there in hopes of finding a solution. Now that being said, breadth first search will find the quickest solution in terms of path connectedness than depth first search. So let's see, I have an example in here. Yeah, I didn't craft a good example here, but so if there's a particular graph that has two ways to get to a solution converging on it, a depth first search might take a longer path to get there and then still find the solution and go, okay, I'm done. Whereas breadth first search always takes the shortest path because, as you recall, it's always looking at every level down from the tree or every edge series out of the original start vertex one at a time. So it will always converge on the shortest piece. And that's an important advantage of breadth first search. And so there you have it. That's really breadth first search and depth first search in an overview. I encourage you to do some web research. There's a lot of information on this stuff. Your book does not cover this very well at all. So please do web research and let's talk about it in the discussions, and I hope that some interesting things will come out.